This is multiple choice problem 6 from the second midterm of Physics 106 from 2024. So here we have a non-conducting rod of length D, and this carries some charge Q. I believe it's uniform. Yeah. Suppose a non-conducting rod of length D carries a uniform distributed charge capital Q. It's rotated with angular velocity omega about an axis perpendicular to the rod, as shown in the figure. So it's rotating this way. This is the pivot point. It's rotating around its bottom point. What's the magnetic dipole moment mu of this rod? Okay. So first of all, there isn't really a current here. There isn't really a current carrying loop here. So what are they talking about? What they're talking about is that you can consider each piece of this rod as a little charge, and then those charges are going to go around in circles, and each of these circles are going to have some magnetic moment, and we have to add those magnetic moments up to find the magnetic moment of this one. This is not really a magnetic moment, but this is the only interpretation that actually comes to my mind. So that's what I'm going to do. Now, to do that, I need to know the current, the effective current passing through this, and at the same time, I need to know the charge going through that. So let's say that this is some, some thickness dx, and it has some charge dq. So this is going to correspond to some di, which is then going to lead to some d mu. Okay, so this mu is going to be the integral of all those d mu's. Now that d mu, so mu normally, the magnetic moment is normally the current times the area. Here our current is infinitesimal, so this is the area times di. This has to be infinitesimal because it arises from the motion of an infinitesimal charge, but the area is going to be finite. So the area is over here, this whole circle. So if I take this, for example, the r coordinate, so this is r equals 0 over here. This is going to be my length. The area is going to be pi r squared. Pi r squared di. Okay, now how do I figure di? Well, di is dq divided by the time span. So the charge that actually moves, and so this is the total charge, and it's going to be the time it takes for this to move over this point. So every period over at any point on the circle, if you, for example, choose this point, over this point, some charge dq is going to pass. It's going to pass, a period passes, and then it's going to pass again, a period passes, it's going to pass again. So this di is in fact is dq by the period. And what is the period? Well, the period is given by this omega. Okay? So the omega is our angular frequency. So the period is going to be 2 pi by omega. So period is 2 pi over omega. So if we invert this, this is going to be pi r square omega over 2 pi dq. Right? Okay, so far so good. Now I need to get some limits for this integration, and I need to make my integration variable compatible with those limits, or vice versa. Either I need to change the function inside and make it compatible with my integration variable, or I change the integration variable and make it compatible with the arguments and the limits. I think it's easier to change this one. This dq is basically this dx times times lambda. Charge density, but lambda is nothing but the total charge divided by the length. So this is dx times q over d, but the dx is nothing but dr. Right? So dx was the thickness of this little piece, but I'm going from r equals 0 to r equals d by adding these little dr's. Those dr's are nothing but dx, so this is in fact equal to dr q by d. So let's put that dq as well. So this goes from r equals 0 to r equals d pi r square omega over 2 pi, and this is q by d dr. Okay. The pi's go away. These guys come out. and the integral can be done. Omega over 2d. So this is integral of r squared, that is r cubed by 3, and this is from d to 0, so at 0 it vanishes, so this is d cubed by 3. One of the d's go away. This is omega q d squared by 6. Right? So this will be the total magnetic moment that's arising from these little loop-like things that are carrying current-like stuff. And this is in fact the answer given in the answer sheet.